D.4, three-element partition. Now we want to solve the general selection problem. First, let us do some preparation. Assume the solution function is available. So we want to describe what is the input and output of the solution function. Here, I call it gen selection with two parameters. The first is the positive integer rank number k. The second is the data, the unordered array that we need to do the selection problem on it. Now, the output, the input is straightforward, but the output, not that simple. The output, because the information we need from the output will be used in our recurrence function call. So that is important. All right. Return an integer array, S array. So what information do we need inside this array? So let me describe it. S0, the first element in the array, index of the k smallest element in A array. That's the first element. But we need more information than that. So that's the first one. All right, yeah. So the k smallest. But remaining elements in this array, we need to get more indices. What are those indices? Indices for those elements in A array whose ranks are less than k. We also need those elements. That information is important because in order to do the partition, we need to do partition. Okay? Divide the problem into two subproblems. So we need to do partition. In order to determine that the partition location, we need these indices. All right. So with that preparation, now we can work on the solution analysis. So let's draw a diagram and try to describe the details of this algorithm. Start from our experience. To solve this problem, we need to use some experience, related experience. So the experience we need to use, you know it, I put it in one of the homework assignment number 1. One of the questions in that assignment. Find the median of 3-element array. That is a very simple one. Find the median of 3-element array. So I think you know how to find it. You know how to find it. So the question is, can we use this result to eliminate some elements? Can we use this result to do partition somewhere, split the original array into 2 parts, and one subarray, one of the 2 subarrays can be eliminated. Then we just work on the remaining subarray. So that is the plan we want to implement. So let me work on the details here. All right. Because in order to use this result, how do we use this result? We divide all the elements in the original array in 3 element groups. Each group 3 elements, 3 element groups. So we have many 3 element groups. Then we can apply the result of this simple, easy problem. Okay? But to make that step easier for us, convenient for us, we just assume n is multiple of 3. N equals 3r. So we can get r 3 element groups. Then we work on it. That's pretty easy. Yeah. All right. So look like this. Yeah. Here you can see for each group, this is one group. The top element is smaller than the middle element. Middle element is smaller than the bottom element. So the middle element is the median of these 3 element group. Here you can see in order to find the median, so here we need 3 comparisons. All right, 3 comparisons. That's the same number of comparisons we need to sort 3 element array. Right? Yeah. To sort any 3 element array, we also need 3 comparisons. So for this small number of element array, find the median and sort it the same number of comparisons. Only for 3. Yeah. If we have more elements in the array, then we need many more comparisons to sort it, then we just find the median. Alright, so now you can see to find all the medians of all the groups, number of comparisons. Each group, 3 comparisons. Later we need to count how many comparisons. Next, this middle row, very special. This middle row, all medians. The medians of all R groups. There are R groups. R. Okay? But in order to make it easier for us, we like to choose R equals an odd number, 2s plus 1. It's an odd number. Why this is better? Because if R is an odd number, there is a middle column right in the middle. Okay? So that would be very good. Okay? For 1, the column really at the middle location. So that would be nice. So that's why we assume that first. Because later, if it's not that, we can do adjustment easily. Yeah. Now we just pick a number with the format that we really want to have. Yeah. All right. So then n equals 6s plus 3. Yeah. All right. So why it is good? Yeah. So you will see because remember, we want to do partition. We want to partition this array, the elements of this array. So we need to find a partition element somewhere in the middle. The partition element, if it is located near the middle, the rank near the middle, then we will get a better performance. So remember that balancing principle. If the partition element is near the middle, then our split, our division of the original array is more balanced. based on the balancing principle, the more balanced division we can do, the better the overall performance. So that's the reason we want to find the special partitioning element somewhere in the middle. Right. So that's why if we use this special form, then we have one column at the middle. Right? Yeah. All right. Next, which special element do we pick for the partition element? This one we pick. Use the median of the medians. So look at all these R medians. In this red circle, we have R medians. Now, can we find the median of these five R medians? R, it's an R number, so we really have a median element in the middle. Okay? Yeah. Theoretically, there exists one element that is the median. Okay? Theoretically, yeah. But remember, we assume this function can return that median to us. Okay? Yeah. By recurrence function call, we can get the median of the medians. This element is very special, so we will use it as our partition element. So that's the reason. That's why we spend so much time work on it, because we want to find that special element. All right, so next, let's continue on that to work on determine the partition element. M star, so I use the notation M star represent the median of the medians. So we select this M star. It is well defined median of the medians. It is clear the meaning, so we can, theoretically, we can find it. Recurrence function call. After that, now we want to look at the partition. What kind of partition we can get? All right. First, with this element we use as the partition element, we want to look at those elements that are guaranteed to be less than M star. Now, here we can assume all the elements distinct. In order to make the discussion a little easier, usually we assume all the array elements are distinct. If later it's not distinct, it's fine. We just do some small adjustment. But in our initial, the first round discussion, so we like to make the situation easier for us. All right. Can you see what are those elements that are guaranteed less than M star? Here, so let me choose some of those elements in our diagram. Is this because this is M star, is this guaranteed to be less than M star? Yes, right? Yeah. All right. How about these elements? Remember when we call this function, it also returns indices of indices. Look at this. Indices for those elements whose ranks less than k. We also return that. Okay? So when we call that function recursively, returns this one, but at the same time we want to return those elements that have the rank less than this one, less than the rank of this element. So we can determine these elements. We know they are less than this element. Okay? So that's the reason we need this. We use it here. Otherwise, we cannot do the partition. Okay? Yeah. So we have that. Based on that assumption, we have that. Is this one guaranteed smaller than that? Yes. Is this one guaranteed smaller than that? Yes. Is this one guaranteed smaller than that? So you can see within the red circle, all the elements at the left-hand side of this M star are less than this M star element. Okay? Yeah. How about these elements? This one less than this one less than that. So then this one also less than the M star. Okay? How about this? Less than this, also less than that. So you can see all the elements here less than M star. Okay? Finally, so let us circle all those elements that are guaranteed less than M star. This circle. This circle. How many elements there? How many? Okay? 2s plus 1. Because this number s plus 1. Remember, r equals 2s plus 1. S here, and a 1 in the middle. So s plus 1. Okay? All right. The top row s plus 1. The bottom only s. Only s. So 2s plus 1. All right. Then, similarly, those elements that are guaranteed to be greater than M star. What are those elements guaranteed to be greater? So similar discussion. This bottom circle are guaranteed to be greater than M star. Similarly, right? Yeah. So we just do the same discussion. Same number of elements in this bottom red circle. 2s plus 1. Okay? All right. So now, it's good because partitioning, we want this M star to separate two groups of elements. So now we already separated 2s plus 1 left-hand side, 2s plus 1 right-hand side. Okay? Yeah. Step 3, remaining elements. Remaining elements, those here, those there, these two circles, greater than or less than, we don't know. Could be greater than, could be less than. We don't know. Okay? Yeah. Those, there are 2s, those elements. S the circle, S the circle. So 2s. But we don't know, compared with the M star, what is the relationship for each element in this part. But we can find them. We just do comparisons. We need to do span some comparisons to get that information. So our next step, we need to determine the rank of M star. What is the rank of M star? We need that information because we want to throw away one of the two subarrays. So you need to know the exact location of the M star so you can throw away one of the two subarrays. Otherwise, you cannot throw away any subarray. So the next step, now we move to this step. In order to determine the rank, so let us do the partition. Let us fix all the unknown relationship, comparing with N star, all the elements. Right now there are 2s elements. We don't know the information comparing with N star. greater than or less than? We don't know. So we need to fix that part. So let's draw this line segment representing the whole array. M star somewhere in the middle. Those parts already, the relationship already known, so we can, identify them first. Part 1 to S, we already know, less than M star, left-hand side of M star. Part 2, those elements 2S plus 1 greater than M star, so we put them right-hand side of the M star. Then the remaining 2S elements, we don't know, but we can do comparison, right? One by one compare with M star. So after 2S comparisons, we can get this. We find A elements are less than M star. Just some number A. B elements are greater than M star. After we do 2S comparisons, we can get those two numbers, little a and a little b. So each one between 0 and a 2S. Okay? Yeah. So we fix that. After that, this M star in place. The rank is now in place. How many elements smaller than M star? How many elements greater than M star? We know those two numbers. So the rank of M star is known, and we can put M star in place. Okay? So that's this step. So now we have the information we need to do the partition. All right. So the last step, we just do the partition and throw away one of the subarray and reduce the problem size. That's the last step of this video. For the analysis part, I will leave to the another part, because today we cannot complete that part. All right, so the last step, how to drop a subarray. Based on the information we have here, we can make that decision easily. So after the partition, we have 3 possible cases. So we go through one by one. The first case, if K equals 2S plus A plus 2, what's that? That's the rank of M star. Rank of M star. Rank number of M star. K equals the rank number of A star. That means the result is the M star element. Selection problem, the answer is that M star element. Okay? So we find the answer. 2, if K less than 2S plus A plus 2, the rank less than M star. That means the element, the key to be searched for should be at the left subarray of M star. Left subarray. So then, to solve it, we call our recurrence function call is, it's in the left subarray, the rank number is still the same as that K. After we reduce the array size, the rank number is still the same. And let's see why here I use C array, because we need to rearrange the elements in the original A array. A array is the original. Now we need to do rearrangements. So that's why we will have, C array. C array. Okay? Yeah. Rearrange original. Otherwise, here we cannot use the original A array, right? Yeah. So that's why we use a different symbol. Yeah. All right, so that's case 2. The last case, case 3, when k greater than 2s plus a plus 2, this time we need to make a change on the rank number. Okay? Because this time k is in the right subarray. So we need to draw the left subarray and end star. We need to draw all those elements. Now, after you draw these elements, then the k number will be changed. We need to subtract all these numbers. So that's why we call our recurrence function call. This time we need to subtract 2s plus 2 plus a plus 2 from k. So that is our new rank number passed to this function. And this time we use that unadjusted C array, but with different indexes. All right. So when you put all these things together, you can implement the details and you can write a program to find the solution. But we need to do analysis. We need to know if this algorithm can give us satisfactory solution. We may not get a good solution. We don't know at this point. So we need to, when we go to the next part, part E, we will do that. Efficiency analysis. All right, so now we finish part